Today in this video, we'll be discussing resting membrane potential. Here we have a cell. Okay, now in order for a cell to create a resting membrane potential, you need to establish a concentration gradient. And the best way to do this is through sodium-potassium pump. And on a sodium-potassium pumps 2 potassium inside the cell and 3 sodium outside the cell. Now I've already written out here the concentrations that are formed when this occurs. Okay, there is essentially more potassium inside the cell, 150 millivolts, and less sodium inside, but there's more sodium outside the cell. Okay, now because there's more sodium or potassium inside the cell actually has these things called leak channels, which makes sodium very permeable, and potassium is actually not very permeable. But because sodium or potassium is permeable, these leak channels work, and sodium or potassium leaves. When potassium leaves, it actually leaves the negative charge behind. Okay, as seen here, right? The negative charge is left behind, but they're still attracted to each other. So as potassium leaves, it actually makes the inside of the cell more negative. Okay, but that is our chemical gradient. But when we take a look at our electrical gradient, remember that there's a ton of sodium outside the cell, and this positive charge actually pushes back on that potassium ion, which forces potassium to leave less. Okay, and now this push and pull, right, this whole push-pull kind of thing gradient, of course, between the electrical and chemical gradients, helps us establish an equilibrium of a negative 70 millivolts for resting membrane potential. Now, we can take a look at how this works and looks at a graph. As potassium leaves, right? As potassium leaves, we establish more negative inside the cell, right? It essentially would decrease our resting membrane potential, but as sodium enters the cell, it would actually increase if sodium was permeable, of course. Now just kind of a closer look and see how that all works in the magnitude of the resting membrane potential. Now, I kind of want to focus more on some equations here. The Nernst equation, specifically, is an equation that helps us figure out the equilibrium potential for just one ion. Okay, so if one ion was just traveling across that membrane, we could be able to calculate what the charge of the cell would be. Just do that one ion. Now, we can take a closer look at the equation. We see that we see the Z right here. That is the charge of the ion. So it's either +1, -1, +2, right? And we multiply this whole portion times by the log of the concentration of the ion inside the cell and outside the cell. Now, I already calculated that for potassium and sodium, as seen here. Now, the equilibrium potential for potassium is negative 95 here, and of sodium is positive 55. But that is a really bad representation of how the ions are going to move across, because there are tons of other ions that will be moving. So that's why we take a look at the Goldman's equation. The Goldman's equation takes into account all the other ions that will be crossing in and out of that membrane, as well as the permeability, which is so important. Okay, and that's just kind of a big overview of those two equations, and we're going to tie that into driving force really fast. Driving force is the resting membrane potential here minus the equilibrium potential that we just calculated for one ion. We're going to take a closer look at sodium. So we take the resting membrane potential of negative 70 minus the 55, which gives us negative 125. And then for potassium, we get negative 70 minus the 95, which gives us plus 24. Now we're going to look at that in the cell and see what driving force does. Sorry, I didn't explain what driving force. Driving force is just how likely or how much an ion's going to cross a membrane, basically. and it helps us determine which way that ion will go. So if we take a look here at sodium, I like to place that charge, that driving force inside of the cell, because it helps us determine essentially which way it'll go. Okay, so if you have a negative 125 driving force, you have sodium here and here. Sodium is a positively charged ion, so it's actually going to be attracted to go inside of the cell with a pretty large amount, pretty large value there. Okay, so sodium will enter the cell in this case. Now, if we look at potassium, it's about, 24. Potassium's positively charged also. These two positives are actually going to repel each other and push potassium outside of the cell. And we can see that the driving force for sodium is a lot stronger for potassium. It just helps us understand what and how the charge of that cell will change, and essentially help us determine action potential further down the road. And that is that for this video. We will talk more about synapse and action potentials in the following.